We want to look at this question related to conditional probability, where we're told that the coin is tossed 2 times, and you want to find the probability that both flips land on heads, given that the first flip lands on heads. So here, the random experiment is toss 2 coins, and let's define our events. Let's define event A to be both flips land on heads. And let event B be first flip lands on head. What we want to find is now, we want to find the probability of both flips land on head, i.e. the probability of A, given that the first flip lands on head, so probability of A given B. So we're interested in this conditional probability. Now, the two ways I will solve this, we'll use two approaches over here. So approach one is going to be, so we're going to do this using two ways. One is going to be using a formula, and the other is going to be using a reduced sample space. So approach one is use the formula. And what is the formula? Let's just look at that. We know the formula is probability A given B is probability A and B. The comma just means and or intersection divided by probability of B. So we're just applying the formula. In this context, what is probability of A and B? Probability of A and B is the probability that both flips land on heads and the first flip lands on heads. So this is essentially the probability both flips land on heads, right? This is this probability. And this is essentially this outcome head-head, right? Because once you have this, then both events A and B are satisfied. The first flip is landing on when both flips land on head, so the first flip is automatically landing on head. And what is the probability of B? The probability of B is probability first flip lands on head. And this includes the outcomes head, tail, and head, right? So this includes outcome head, tail, and head, right? Because the idea is that the first flip should land on head, the second flip could be a head or tail. So both outcomes are incorporated by event B. Now, if we calculate these probabilities, the upper probability turns out to be 1 by 4 and the lower probability turns out to be 2 by 4. Why? Let's just quickly look at that. We know our sample space is this, right? In this case, we're tossing 2 coins, so the sample space is that you can have head on first and head on second. You can have head on first, tail on second. You can have tail on first, head on second, or you can have tail on both, right? This is the sample space when you're tossing 2 coins, all the possible outcomes. Now here the key is all outcomes are equally likely. This is the key word here, all outcomes are equally likely, right? This is the key, equally likely. Now we know A intersection B, this event, which is in the numerator, this is the probability of A and B. This comma means and or intersection, right? So this does mean that. So we're essentially looking at the probability of A intersection B in the numerator. So this event A intersection B is essentially when they both flips land on head, right? So this just has this one outcome, head, right? And we know B event is made up of these outcomes, like we saw head, tail, and head, because the first outcome has to be head, the second output can be a head or tail. Now here we just want to quickly recall something. Let me just write it here. Recall, if all outcomes are equally likely, again the key word is if all outcomes are equally likely, right? This is the key here, likely, then probability of A is just number of outcomes favorable to A divided by total number of outcomes in sample space. So in this particular example, like we said, in our sample space, every outcome is equally likely. You have two, so this should be a fair coin, right? So this essentially be a fair coin. So we are using a fair coin. So every outcome in the sample space is equally likely, right? Because it's a fair coin, all outcomes are equally likely. So we can find the probability of each of these events as number of outcomes favorable to those events divided by total number of outcomes in sample space, because this particular definition of probability only works at equally likely outcomes, which we have in this case with a fair coin. So probability of A and B is just simply the number of outcomes favorable in A intersection B, which is one, right? There's just one outcome, right? Where both flips are heads, right? So that's why we have one here. Divided by total outcomes in sample space, which are 1, 2, 3, 4. Similarly, probability of B would be number of outcomes favorable to B, which is 2, divided by total number of outcomes in sample space, which is 4, right? So we found each of these probabilities in the numerator and denominator in our formula using this that you by dividing the total number of outcomes favorable to the event divided by total number of outcomes in sample space. And keep in mind this only applies when all outcomes are equally likely. So that's the key. And in this case, that was true because we had fair coin. So now once you simplify this just turns out to be 1 by 2. Right, so this is approach 1. Let's clear this. Now let's look at approach 2. So this is one way we could find this conditional probability using the formula. Now we want to use another approach. The second approach is going to be shrink sample space. What do we mean by shrink sample space? Right, the first approach is just apply the conditional probability formula, right? Second approach is shrink the sample space. So essentially what you want to do is you want to find the reduced sample space. Now, what do we mean by reduced sample space? What we mean is remove what is not a possibility. Remove what is not a possibility. In this case, we are given first flip lands on head, right? We're told okay, we're given first flip lands on head. We're told, right, the first flip lands on head. So we're given event P, right? Event P, right? We're told this, right? Given. So we already know the first flip lands on head. So what we can do is, so remove all outcomes if first flip is not head. So remove all outcomes in the sample space. So remove all outcomes from, remove all outcomes in sample space. So remove all outcomes where first flip is not head. So remove what is not a possibility. We're told that the first flip is head, so we can remove all the outcomes in the sample space where the first flip is not a head and find a reduced sample space. So we know our sample space was this, right? Our sample space was head, head. It was head, tail. It was tail, tail. Because all of these are possible, right? A sample space set of all possible outcomes. And when you toss two coins, all of these are possibilities, right? So, but like we said, we're already given that the first flip lands on head, so we'll remove what is not a possibility. This can be possible because the first flip lands on head. This can be possibility. This cannot be, and this cannot be possibility. So a reduced sample space is just head, head, right? This is a reduced sample space and head tail. This is a reduced sample space, right? Because we remove whatever is not a possibility. These are not possible because we already told the first flip has to be head. So the reduced sample space is head, head, head tail, taking into account the observation that were given. Out of this reduced sample space now, out of this reduced sample space, we can now see how many outcomes. We can now see how many outcomes have both heads. So given this reduced sample space, we can now find event A. We can now see how many outcomes have both heads. Because remember what we wanted to find was the probability that both flips land on heads given that the first flip lands on heads, right? So we've already reduced our sample space by removing what is not a possibility and only considering the outcomes where the first flip lands on head. Now we can just find, now we just count the total number of outcomes that have both heads, which is just 1. So this is just going to be 1 divided by 2. This probability of A given right? So we first reduced our sample space by removing what is not a possibility, which is all those outcomes where the first flip is not a head. Now, out of this reduced sample space, we want to find the probability that both flips are heads, and so now reduced sample space, that's just one possible outcome. So the probability is just 1 by 2. And again, we can find probabilities like this by dividing number of favorable outcomes by total possible outcomes only when all outcomes are equally likely. And in this case, this was true because we were looking at a pair coin, right? So just a warning here. So just a warning, we can only find probability of an event as number of favorable outcomes to the event divided by total number of outcomes in sample. Oh, sorry. Divided by total number of outcomes in sample. Divided by total number of outcomes in sample space if we have equally likely outcomes in sample space. And in this question, we did because of the fair coin. If we have equally likely outcomes, so just keep in mind whenever you're trying to find any probability using this number of favorable outcomes and number of total possible outcomes, this only applies when you have equally likely outcomes, which you definitely have if you have fair coin and fair dice. So we learn how can we find conditional probability using two approaches. The first, you can use the formula. The second, you can work with the reduced sample space. In either case, if you are applying this formula, just make sure you have equally likely outcomes.